3. So we start by the definition of divisibility. So when we say one integer is divisible by another integer, when there exists integer c such that b is equal to ac. And the symbol is this. This means a divides b. And if a does not divide b, then this is the symbol. So simply we strike the divide sign. And next, with the definition of divisibility, we have definition of GCD. What is GCD? Greatest common divisor. So for to find GCD, we want that at least one of the number is non-zero, because if both are zero, then we have infinitely many common divisors. So it is impossible to find the greatest one. So to find GCD, we want that at least one of them is different from 0. And here it is denoted by the symbol D, and it has to satisfy two properties: that it is a common divisor. If there is another common divisor, then D is larger than that, because D is the greatest common divisor. Now with this knowledge, we have some results. If A and B not both 0, then there exist x and y such that GCD may be written as linear combination of A and B for some x and y. And if A and B are relatively prime, then above theorem says then 1 is equal to AX plus BY, because relatively prime means GCD of AB is 1. So here we will put 1. Corollary 1. If GCD of A and B is D, then GCD of A by D and B by D is 1. And here we will note that A by D and B by D are not fractions, they are integers, because D divides A and D divides B. And another result is, if A divides C, B divides C, GCD of AB is 1, then their product will divide C. And last one is, if A divides BC, GCD of AB is 1, then A will divide C. So with this knowledge, we have problem set 2.3, and the first question is use mathematical induction to establish this result. So we use mathematical induction. Case 1, for n is equal to 1, so it becomes 4 power 1 plus 1, 5 power 2 times 1 minus 1. That is 4 square 16 plus 5 21. So 21 is divisible by 21. Result is true for n is equal to 1. Case 2, let result is true for n is equal to k. Means 4 power k plus 1, 5 power 2k minus 1 is equal to 21 m. Now case 3, we prove for n is equal to k plus 1. What is to prove here? To prove that 4 power k plus 1 plus 1, 5 power 2 into k plus 1 minus 1 is integral multiple of 21. This is to prove. To prove this, we start from the left hand side, that 4 power k plus 1 into 4, 5 power 2k minus 1 into 5 square. So we know we want to use this result to make it this form. What will we do? We will add 5 power 2k minus 1 into 4 and subtract 5 power 2k minus 1 into 4. So taking common from the first part, 4 common, we have 4 power k plus 1, 5 power 2k minus 1. And the second part, we can take common 5 power 2k minus 1. So in the bracket we have 5 square 25 minus 4, which is 21. And very easily this is 21m, and here we have 21 itself. So very easily we can take 21 common, and we have 4m plus 5 power 2k minus 1. So which is an integer, so it's a multiple of 21. So result is true for k plus 1. So hence by mathematical induction we get the desired answer. For arbitrary integer a, verify 2 divides a into a plus 1 by division algorithm. We know when we divide any number by 2, it is of the type either 2k or 2k plus 1. So case 1, this a plus 1 is of the form 2k into 2k plus 1. So very easily we can see it's a multiple of 2. So it is divisible by 2. So 2 divides a into a plus 1. So in the second case, equals 2k plus 1, and here we have 2k plus 1 plus 1. So easily we can take common 2 from the second bracket. This is 2 times 2k plus 1 k plus 1. So here also 2 divides a into a plus 1. So from both the cases we get the desired answer. So in the second part we want to prove 3 divide this. So by division algorithm, when we divide any integer by 3, it is of the form 3k, 3k plus 1, 3k plus 2. So we have 3 cases. So in the first case, when we put 3k, a plus 1, a plus 2 becomes 3k, 3k plus 1, 3k plus 2, and very easily we can take 3 common, k, 3k plus 1, 3k plus 2. So it's a multiple of 3. So in the second case, when we put 3k plus 1, a plus 1, a plus 2 becomes 3k plus 1, 3k plus 1 plus 1, 3k plus 2. And in the third case, 3k plus 1 plus 2, 3k plus 3. So we can easily take 3 common from here. 3 times 3k plus 1, 3k plus 2, and here we have k plus 1. So again it's a multiple of 3. So 3 divides this. So in the last case, a plus 1, a plus 2. So we have 3k plus 2, 3k plus 3, 3k plus 4. So we can take 3 common from the second factor. So this is 3k plus 2, k plus 1, 3k plus 4. So once again, 3 is a common factor here. So in all the 3 cases, we can see that 3 divides a plus 1, a plus 2. So from these two, we can also see that product of 2 consecutive integers is divisible by 2. Product of 3 consecutive integers is divisible by 3. So we can extend this result to bigger number also. So next, once again, we have to check divisibility by 3. So again, when we divide any number by 3 by division algorithm, it is of the type 3k, 3k plus 1, 3k plus 2. So in the case 1, a 2a square plus 7 is 3k, 2 times 3k square, that is 9k square, plus 7. So you see it's a multiple of 3. So we are done. In the second case, a 2a square plus 7 becomes 3k plus 1 2 times 9k square plus 1 plus 6k plus 7, that is 3k plus 1. So this is 2 nines are 18k square plus 12k plus 2 plus 7 9. So very easily we can take 3 common from here. So it's a multiple of 3 again. And in the third case, a 2a square plus 7 is 7, and it becomes 3k plus 2, and here we have 18k square, 24k plus 2 4s are 8 plus 7 15. So once again we can take 3 common from here. So from all the 3 cases we get 3 divides this number. Next question, if a is odd then 32 divides this. We know square of an odd integer is of the type 8k plus 1. So putting a square as 8k plus 1, a square plus 3, a square plus 7 becomes 8k plus 1 plus 3, 8k plus 1 plus 7, that is 8k plus 4 and 8k plus 8. So we can take 4 common from here and 8 from here. So it becomes 4 8 the 32 times 2k plus 1 k plus 1. So it's a multiple of 32, means 32 divides this. So next question, once again a and b are odd integers. So we know that square of an odd integer is of the type 8k plus 1 as previously written. So here a square is 8k1 plus 1, b square is 8k2 plus 1. So given a power 4 b power 4 minus 2 becomes 8k1 plus 1 square, 8k2 plus 1 square, minus 2 squaring. So we get 64k1 square plus 16k1 plus 1 plus 62k2 square, 16k2 plus 1 minus 2. So 1 cancel with 2, and very easily we can take 16 common from the 4k1 square plus k1, 4k2 square plus k2. So we can easily put this as 16k, which imply 16 divides a power 4 b power 4 minus 2. Desired answer. We know that square of an integer leaves remainder either 0 or 1 when divided by 4, and further it leaves remainder 0 if even number leaves remainder 0, and square of odd integer leaves remainder 1. So given in the statement we have two odd integers, let a and b be given odd integers, means a square plus b square, and as we know square of an odd integer leaves remainder 1, so it is of the type 4k1 plus 1 plus 4k2 plus 1. So very easily we can take 4 common, k1 plus k2 plus 2, or we may write 4k plus 2. That means sum of squares of two odd integers is of the type 4k plus 2. But for a square, it is of the type either 4k or 4k plus 1. Means 4k plus 2 is never a perfect square. So hence we get the required answer. Prove that product of 4 consecutive integers is 1 less than a perfect square. Let product of 4 consecutive integers be a plus 1, a plus 2, a plus 3 equals. So first we multiply these two, a into a plus 1, so we get a square plus 5a plus 6. Now we multiply these two, so we get a cube 5a square 6a, and by multiplication with 1, which further equals to a times a cube 6a square 11a plus 6. Further multiplying with a power 4 6a cube 11a square 6a. Now we try to convert this as a perfect square. For that we will add 1 and subtract 1. So this becomes square of a square plus 3a plus 1 square minus 1. So very easily we can verify this square, and it is 1 less than a perfect square, hence the answer. Next, establish that difference of two consecutive cubes is never divisible by 2. Let difference of two consecutive cubes a plus 1 cube minus a cube equals, now opening the cube, it is a cube plus 1 plus 3a times a plus 1 minus a cube. So this is a cube plus 1 plus 3a square 3a minus a cube. So this will cancel, and we have 3a square plus 3. So we have, taking 3a common, a plus 1 plus 1. So very easily we can see that this is product of two consecutive integers, and we know 2 divides a into a plus 1. So a into a plus 1 is 2k. So putting this value becomes 6k plus 1, which may further be written as 2 times 3k plus 1. We know multiple of 2 is always even, plus 1, so this number is always odd. If it is odd, then 2 will not divide a odd number. Hence, difference of two consecutive cubes is never divisible by 2. Desired answer. Prove that for a positive integer n and any integer a, GCD of a and a plus n divides n. To prove this, let d be the GCD of a and a plus n. What is to prove here? D divides n. So by definition of GCD, we have d divides a, d divides a plus n. And also we know that if d divides a and d divides a plus n, d divides their linear combination, ax plus a plus ny. Now choosing values such that we are left with n only. So very easily we can choose x is equal to -1 and y equals to 1. So it becomes -a plus a plus n, which imply t divides n. Hence the answer. And in the second case, prove GCD of a and a plus 1 is 1. We take n is equal to 1 in the first case. So it becomes GCD of a and a plus 1, 1. So which further imply that GCD of a and a plus 1 has to be 1. Answer. Now to prove, for any integer a, show that GCD of these two numbers is equal to 1. Let GCD of 2a plus 1, 9a plus 4 is d other than 1. So by definition of GCD, d divides 2a plus 1 and d divides 9a plus 4. And also we know that d divides their linear combination, 2a plus 1x plus 9a plus 4. So we choose x is equal to 9 and y equals to minus. D divides, we put 9, x as 9, 18a plus 9, and y as -2, minus 18a minus 8. So 18a cancel, so we are left with d divides 1. Because d is GCD, because d is GCD, it is always positive. So d divide 1 imply d equals to 1. Answer that a is arbitrary integer, then 6 divides a into a square plus 1. Now to prove this, there are two ways. Either we use division algorithm for 6, or we prove this result for two relatively prime integers which are factors of 6. So we write 6 as 2 into 3, because now we prove 2 divides a into a square plus 11 and 3 divides a into a square plus 11, because GCD of 2 and 3 is 1, which imply their product will divide a into a square plus 11. So we prove this in two parts. First we prove this part, and then in the second part we prove this. So in the first part we have two cases, that when we divide any number by 2 by division algorithm, either it is 2q or 2q plus 1. So in case 1, when we have 2q, so a into a square plus 11 is of the type 2q. We have 4q square plus 11, and very easily we can take 2 common, q into 4q square plus 11, which is 2k. Now in the second case, a square plus 11 becomes 2q plus 1, 4q square plus 1 plus 4q plus 11. So once again, from the second bracket we can take 2 common, so it is again of the type 2k. So we get 2 divides a into a square plus 11. So in part B, now we have three cases, 3q, 3q plus 1, 3q plus 2. So in case 1, so it's the trivial case, that a into a square plus 11 is 3k, 3q, 9q square plus 11, which is multiple of 3. So in the second case, we have 3q plus 1 and then squaring 9q square plus 6q plus 1 plus 11, 12. So very easily we can take 3 common. It's again 3k. And in third case, we have 3q plus 2 and squaring 9q square plus 12q. 2 square is 4 plus 11, 15. So we can again take 3 common from this factor. So we have proved this, which imply this. Hence the answer. A is not divisible by 2 or 3. We want to prove that 24 divides a square plus 23. Now to prove this, we take two relatively prime factors of 24, that is 3 and 8. And so we divide 3 divide this and 8 divides a square plus 23. As we know, GCD of 3 and 8 is 1, which imply their product divides this. So by this method we will get the result. First we prove that 3 divide this. So when we divide any number by 3 by division algorithm, it is of the type 3k, 3k plus 1, 3k plus 2. But here one more thing we are given, that number is not divisible by 2 or 3. So this will not be the case. We are left with only two options, 3k plus 1 and 3k plus 2. Let's see. A square plus 23. In case 1 is 9k square plus 6k. 1 plus 23 is 24. So which is a multiple of 3. So in the second case, we have a square plus 23. It is 9k square plus 12k. 4 plus 23, 27. So which is again multiple of 3. So which means 3 divides a square plus 23. Now second case, 8 divides this. So when we divide any number by 8, it is of the type 8k. 8k plus 1, 6 plus 7. But again, using the way that it is not divisible by 2 or 3. So this is not the case, this is not the case, this is not the case, this is not the case. So we are left with only 4 options. So in a similar way, like in case 1, we have a square plus 23 as 8k plus 1 square plus 23. So it will be 64k square plus 16k plus 23 plus 1, 24. So we can take 8 common, so which is 8q. So similarly for 8k plus 3, 8k plus 5 and 8k plus 7. So we will get that 8 divides a square plus 23. So as GCD of 3 and 8 is 1, we get 24 divides a square plus 23. Hence the answer. So we know if GCD of a and b is 1, there exist x and y integers such that 1 is equal to ax plus by. And similarly, if GCD of a and c is 1, there exist integers u and v such that 1 is equal to au plus cv. Now to prove this result, what will we do? We just multiply these two, left hand side with left hand side and right hand side with right hand side. So we have 1 is equal to, this is taking a common, this is aux. So a common, this is cvx, and from Second factor, again a common, we have BYU and other BCYV. So what we can see that linear combination of A and BC is 1, which imply GCD of A and BC is 1. Answer. GCD of AB is 1 and C divides A. We have to prove that GCD of B and C is 1. Now, to prove this, we let D is GCD of B and C. So by definition of GCD, D divides B, D divides C. Also given C divides A. Now combining these two, what we get? D divides A. Now what we have? D divides A and D divides B, which further imply D divides their GCD, and we are given this GCD as 1, and because D is a positive integer, the only possibility that it will divide 1 is 1 itself, means GCD of BC is 1, hence the answer. So we have to prove if GCD of AB is 1, GCD of A square B square is 1. So for that, let D is GCD of A square and B square. So by definition of GCD, D divides A square and D divides B square. So here we need two properties. Let me write those properties. The first one is the smallest positive divisor strictly greater than 1 of any positive integer strictly greater than 1 is prime. And second property is if P divides A power n, then P will divide A. So we use this here. Now D divides A square, D divides B square. So there exists P belong to Z such that P divides D. And further, which imply P divide A square and P divide B square. And if P divide A square imply P divides A, P divides B. If P divide A and P divide B, P divide GCD of AB, which means P divides 1. So we get a contradiction here. So our supposition is wrong that D has to be 1, that GCD of A square and B square is 1. Answer. Now to prove this result, we need to take an identity, that is x power k minus 1 is x minus 1, x power k minus 1, k minus 2, x plus 1. So given D divides n, which imply n is dk. So we start with 2 power n minus 1, which is actually 2 power dk, and we write it as this minus 1, and using this identity here 2 power d minus 1, and this is 2 power d power k minus 1, 2 power d power k minus 2, 2 power d plus 1. So very easily we can see that this is integral multiple of 2 power d minus 1, imply 2 power d minus 1 divides 2 power n minus 1. Hence the result. Now its application is verify that 31 divides 2 power 35 minus 1. So we can easily write that 31 may be written as 2 power 5 minus 1, which divides 2 power 35 minus 1, because 5 divides 35. Answer. Because d divides n, so 2 power d minus 1 will divide 2 power n minus 1. Answer.